Hi there, my name is Dwayne Habecker. I am one of the math coordinators from Merced County Office of Education, and the purpose of this video here is going to be for us to give you a brief intro of what CRA is. What is the CRA approach? This video is going to really limit our focus on TK through 5th grade as our focus. We do have a middle school and a secondary video for you if you are interested, but right now we're going to focus on TK-5. The purpose of this video is really to kind of help you understand what is CRA, why is it important, and then give you a brief overview as to some examples of what it might look like to employ CRA in your math time. This is just a brief overview. We're going to go into greater detail throughout the year as we dig into specific math topics throughout the year. So let's get started. Now, all of the materials are available at this this link right here. So go ahead and pause the video and go to it. It is case sensitive, so make sure you get those capitals and those lower cases correct. I want to give you a brief overview first of what is the MCOE vision for math learning. Our vision is that every student is enthused about mathematics. They see the value and the beauty of mathematics, and they're empowered by the opportunities that mathematics affords. Now, that's our vision. Now, what are we going to do to get there? We use the mathematics hierarchy of needs. It's a step-by-step roadmap based on Maslow's hierarchy of needs that guides us towards the ultimate goal, which is that top of that pyramid, which is math literacy. And as I said, it comes from Maslow's hierarchy of needs, where each of his levels of needs were mathematized, and where physiological needs of Maslow becomes material needs in mathematics. So the idea is in Maslow, you got to begin by the basics: food, water, shelter. And in mathematics, that looks like what are the basics? Well, the basics are having essential standards, having a powerful curriculum, and importantly, having a teacher who has the mathematical knowledge for teaching. This teacher who has content knowledge, but also pedagogy knowledge. And then in Maslow, once you've got your physiological needs taken care of, you grow up, you build up towards safety and security. Well, in the math world, once you've got your basic needs met, now we create that safety and security through what we call mindset and culture, where all students can learn, where mistakes are normalized as a natural part of that learning process. Then in Maslow, once you're safe and secure, you take care of your love and belonging. In the math world, we call that student-centered instruction, where students are immersed in a meaningful discourse that promotes conceptual understanding, procedural fluency, problem solving, and application. And it's where the students are doing most of the academic discourse, meaning they're doing most of the learning. Then in Maslow, once you've taken care of your love and belonging, we want to achieve self-esteem, confidence, achievement, and respect for others. We call that in the math world equitable assessment, where students are provided meaningful feedback and intervention that allows them to grow on their mathematical journey. And then in Maslow, he says, all right, once you've done all that, you've reached the top, and we call that self-actualized. In the math world, we call that you are now mathematically literate, where students are confident problem posers and problem solvers. So this is our roadmap for how we are always thinking about how do we journey towards helping a community become full of confident problem posers and problem solvers. Now, each of these layers can be achieved in a variety of different ways. This video is really going to dig into that CRA approach, which lives in the mindset and culture. It's this approach to instructing math instruction that really demonstrates that all students can indeed learn mathematics, but the difference might be some students do it through the C, some do it through the R, and some do it through the A. And I'll give you insight as to what that means in a little bit. Now, in order for us to do that, we need to help also us learn some content knowledge, because CRA is probably not the way you and I were taught mathematics when we were young. And so we're going to have to do some math learning as well on our journey towards implementing the CRA approach in our math classrooms. So CRA is predicated on this idea that visual math improves performance. There's a tremendous amount of evidence out there that says when we employ visual representations as a part of our math learning and teaching, students learn better. We've got tons of evidence. Some of it's you can pull from it from UCubed. It's a wonderful website. From this one, I can't remember what IES stands for, but the WWC stands for What Works Clearinghouse. I think it's the Institute of Educational Sciences, maybe IES. Anyway, tons of evidence that says when we employ visual representation, students learn better. And that's really where CRA comes from. CRA stands for Concrete Representational Abstract. And Concrete Representational Abstract, CRA, it's a really highly effective teaching progression that allows students this opportunity to develop a deep and profound understanding of the concepts that they're learning rather than just through rote memorization. And CRA is especially effective when we're working with English language learners and students with learning disabilities. CRA is just profoundly important. Now, what does CRA stand for? C stands for concrete. That's where the teacher begins using manipulatives as a way to demonstrate this conceptual understanding. R stands for pictorial representations, R, representation. In some countries, instead of calling it CRA, they call it CPA, Concrete Pictorial Abstract. But in the United States, a common phrase, common word is CRA, Concrete Representation Abstract. So that R stands for the use of pictorial representations to represent those concrete manipulatives. And lastly, A stands for abstract, where the students are now using only numbers and symbols to represent their thinking. I want to make sure that I'm not misleading us into thinking that CRA is this process that happens in sequence. Actually, it kind of is introduced in sequence, first concrete, then pictorial representation, then abstract. But really, all three phases of learning are really happening simultaneously. And let me give you an idea of what this might look like. So imagine the horizontal line is time. Time might be a day, it might be a week, or it might be a month, but time is ticking, and that's the horizontal axis down at the bottom. Now, initially, the teacher is going to introduce something, probably through the concrete. And so you've got your C. And so right now, all the students are using manipulatives to demonstrate their understanding and to develop that understanding of whatever concept you're trying to teach. But eventually, some student is going to say, hey, teacher, do I really have to keep using these manipulatives? And you as the teacher might say, well, I don't know. Do you have a suggestion? Do you have some sort of idea of what you might do instead of building with manipulatives? And the student might say, well, yeah, I got an idea. Let me draw pictures. And now all of a sudden you've got your class in two not necessarily equal groups. Some students are still in the concrete phase, while other students have advanced towards the pictorial representation, and they're using pictures to represent the manipulatives that they were previously using. And then some time will pass, and then eventually a student will say, hey, teacher, do I really have to keep drawing all these pictures? And you say, I don't know, do you have a suggestion? And the student will say, yeah, instead of me drawing 8 cubes, can I just write the number 8? And you as the teacher say, wow, that seems pretty lazy, but go ahead. And now you have a class in 3, not necessarily equal groups. Some students are still in the concrete, some students are in the pictorial representation phase, while other students have pushed into that abstract phase. Now it's important that you know that each lesson, you're teaching the same lesson to all students. You are not teaching 3 separate lessons, one lesson for the C, one lesson for the R, and one lesson for the A. That's not what's happening in the CRA approach. In the CRA approach, all students are receiving the same high rigor lesson. The difference, however, is the students kind of self-differentiate as to how they demonstrate their understanding of the concept. Some students are using the C, some students are using the R, and some students are using the A. Time continues to tick, and eventually you have guided all of your concrete students into just the pictorial phase, and then eventually all your pictorial representation phase students will navigate and evolve into just the A. And so that's what we call the arc of development. Now, this arc of development might happen over the course of a day. It might happen over the course of a week. It might happen over the course of a year or multiple years. An example of this is 3rd grade, where division is introduced in 3rd grade as a concrete representation, and then we don't expect long division to be understood at the abstract level all the way until 6th grade. So it's a 3 or 4 year journey for a student to move from this concrete phase all the way to the abstract phase. Not everything is a 3 or 4 year journey. Sometimes you may begin in the concrete phase at the beginning of the week, and you might end in the abstract phase by the end of that same week. So the duration of time really depends on the topics that you are in the process of teaching. So why is CRA so stinking important? Well, CRA is so stinking important because CRA allows the teacher and the student to focus on building conceptual understanding. Rather than us jumping straight to the abstract formulas and rules that students are expected to just memorize, CRA allows us to help the students develop a deep understanding of what's going on. It's that deep conceptual understanding that forms the foundation to allow students to then become procedurally fluent. And so over time, students become skillful in using these procedures flexibly as they go from that C to the R to the A. So that's what it is, why it's important, but let's continue on. Why is CRA so important? When we have these 3 representations, concrete, pictorial representation, and abstract, students are allowed to use one of these phases of understanding to help them deepen their understanding of the other 2. A student may use her understanding of concrete in order to understand pictorial and abstract representations, or another student may use her understanding of the abstract rule to deepen her understanding of what the pictorial representations mean and how we might represent that in a concrete world. So the idea is these 3 representations allow students to kind of move fluidly through these things, developing a deeper understanding of the mathematics. But the neat thing is, NCTM doesn't just have these 3 things. So CRA is actually bigger. CRA also includes the contextual representation and the verbal representation, which just increases the number of connections that students are able to make. And the more connections students are able to make, the deeper the understanding, and the more likely a student is going to be able to find one of these representations to hold on to as their base, so that they can use that base understanding to deepen their understanding of the other representations. In fact, you can even go from a concrete to another concrete, or from a pictorial representation to another pictorial representation. So we've just got tons and tons of these connections that students are able to make. And what's really cool about these connections is they're tied to verbs. Concrete is build it. Pictorial is draw it. Abstract is write it in numbers. So we've got these verbs. Contextual says write a story about what's going on. And lastly, verbal is to talk about it. So when we attach these verbs to these representations, we can see that it's the students who are doing the work rather than the teacher who's doing all the work. All right, so that's why CRA is so important. And all of this sits nicely on Silver and Marzano's work, which involves comparing and contrasting. And what Silver and Marzano have long known is that strategies that engage students in comparative thinking had the greatest effect on student achievement, leading to, in Silver's case, in his study, leading to an average percentile gain of 45 points. Basically, the story is the more we get students comparing and contrasting between all of those representations, the better students are going to learn. So that's what CRA is and why it's so important. So let's go into some examples. Let's start with kindergarten. And with kindergarten, we might simply have something as simple as 2 cubes and 3 cubes, and there's our concrete. And then students, and in this case, we might be adding, we might be comparing numbers. At this point, it doesn't matter. We're just representing a number. Now, what does that look like in the representational phase? Well, students might be drawing pictures of their cubes. In this case, we're putting it inside a number bond as well. And then lastly, what does that look like in the abstract phase? It looks like 2 and 3 right there in another number bond, but this time instead of using the pictures, we are representing those quantities with symbols, 2 and 3. We haven't even gotten to the actual addition where we, of course, represent these as 5. But that's a simple idea of how in kindergarten we move from the concrete phase to the pictorial representation phase to the abstract phase. In the longer journey of that arc of development that we talked about earlier is this K2 trajectory. So it's K1, 2, 3 grade levels where we're really helping students deepen their understanding of addition. Imagine we're doing 9 plus 6. Now that's a little bit advanced for kinder, but let's just roll with it for a moment. This important trajectory is there's really 3 stages of solving 9 plus 6. First, we might do count all, where a student creates a pile of 9 cubes and then creates another pile of 6 cubes and then begins with the number 1 and counts all 15 cubes. And that's stage 1. That tends to be a kindergarten stage. But by the end of kindergarten and going into first grade, we want students to be employing a stage 2 solution strategy for 9 plus 6. That's the count on, where the student might start with the number 9 in their head and say 9, and then count on her fingers, 10, 11, 12, 13, 14, 15. And when I hold up 6 fingers and say the number 15, I know that the answer is 15. Now, folks, stage 2 is where a significant number of our students get stuck because it's a very seductive strategy. It's very fast, very effective. Unfortunately, what it does is it stunts a student's ability to develop automaticity and, using a strategy. kind of like memorization, but something better, automaticity. And stage 2 is so seductively easy that we often get stuck there. Stage 3 is where we want to get to, where students are now using a strategy. Stage 3 oftentimes feels a little slower than stage 2, but it's a necessary stage for developing that deep fluency that we're after. And what stage 3 looks like is where students are using some sort of strategy. In this case, a student might say, well, 9 plus 6. Well, 9 is really close to 10. So I'm going to take 1 from that 6 and give it to the 9. So now I have 10 and 5, which is super easy to do, which is 15. Now, what does that look like? So let's do that real quick. So in the concrete phase, let's show what that concrete phase is and what that representational phase looks like, and then what that abstract phase looks like. So let's go over here. And so what I've got right here is I've got a representation of my 9 right here and my representation of my 6 over here for that 9 plus 6. And there's my 9 plus 6 over here on my little iPad on the right. And on the left, students are looking at this 9 plus 6, and they're saying, well, what is that 9 plus 6? Well, I can take 1 from this 6, and I can move it over to the 10. So what does that look like? Now, that's the concrete phase, and I can see that the answer is 10 plus 5, which is 15. So 9 plus 6 is the same thing as 10 plus 5. Now let's look on the right side on my iPad over here. What does that look like pictorially? Well, pictorially, we may have a student saying, okay, well, there's my really ugly 10 frame. I'm going to have a second one right here, and let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. All right. And so there is my pictorial representation. And the student might say, well, I'm going to take this dot from the right, and I'm going to move it over here to the left. And there is my pictorial representation. So I'm going to actually even just draw some sort of arrow representation to say something got moved over. Now, what might that look like in the abstract phase? Well, in the abstract phase, a student might say, well, I had 9 plus 6, but I recognize that that 6 is 1 and 5 because it was over here. Here's the 1 and there's the 5. And I gave the 1 to the 9. And so 1 plus 9 is 10. And that's this guy way over here. And so now I have 10 plus the remaining 5, which is 15 right there. And so we have it in the concrete phase over here on the left side, 9 plus 6, we move 1 over. Then on the iPad, we had it in the pictorial phase right here, where we were moving this guy from here way to the left. And then lastly, we had that abstract phase. So now you're seeing all on one screen, the C, the R, and the A. And so there we go. And so you've got your concrete phase, you've got your pictorial representation phase. Now, I happen to, in this demo, use 10 frames. I could have used kind of like base 10 blocks. I could have just used cubes to represent that 10 and the 5 right here. And then we've got, of course, the abstract, the symbols. Now, representing subtraction, we have that same 3 phases: count all, count on, and then use a strategy. I'm going to jump straight to use a strategy at this point because I think you get the idea. So I'm going to go straight back to our iPad on the right, which is 12 minus 9. And on the left, let's create that. So I'm going to create 12. All right. And so the idea is, how do we represent 12 minus 9 using some sort of concrete, pictorial, and abstract, but specifically using that stage 3, using some sort of strategy? All right, so let me quickly fill in a couple of 10 frames for the right side. Now, the idea would be to say, well, I've got 12 minus 9. And is it easier for that 12 minus 9, is it easier to take this 9 away from the 10, which is on the left side, or is it easier to take the 9 away from the 2? All right, and that's a weird question to ask, but we want students to recognize that 12 is broken up into 2 parts, a 10 and a 2, and that if we're going to take away 9 away, it might be easier to take 9 away from the 10, because we know our partners to 10. That when we take 10 and take away 9, that's going to leave just 1 cube left over. And then all of a sudden I can see altogether I now have 3. So 12 minus 9 is 3. So that's what that looks like in the concrete world. I started with my 12 right here. 12, and I need to take away 9. Is it easier to take 9 away from the 10, or is it easier to take 9 away from the 2? Well, it's easier to take 9 away from the 10. That leaves me with 1, and 1 plus 2 is 3. So now, what would that look like in the pictorial representation phase on my iPad? Well, if we're going to do 12 minus 9, is it easier to take that 9 away from the 10? Or is it easier to take that 9 away from the 2? Oh, well, it's easier to take that 9 away from the 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I can see that I have 1 on the left and 2 on the right for a total of 3. So what would this look like? So that's the pictorial representation phase. What would that look like in the abstract phase? So the abstract phase is 12 minus 9. And I know that 12 is really 10 and 2. And then is it easier to take 9 away from the 10? Or is it easier to take 9 away from the 2? It's easier to take 9 away from the 10. So 10 minus 9 is 1. And then we have this 1 plus this 2. So 1 plus 2 equals 3. So 12 minus 9 is 3. So the idea is, that seems like a lot of work. And indeed it is, and it is absolutely not our destination. Our destination is actually to have students kind of develop some fluency, procedural fluency, some automaticity, but we're going to get there not through rote memorization. Rather, we're going to get there through the use of a strategy in the abstract, a stage 3 strategy in the abstract. And what you just saw, let's see, right here, is you saw us journey on that stage 3 strategy, starting with the concrete, and then moving to the pictorial representation, and lastly getting to our abstract representation. And this arc of development from the concrete all the way to the abstract may be several weeks at the first grade level. All right, so now, and that's what it quickly looks like all on a single screen on your PowerPoint that you have access to. Now let's just keep going. In third grade, an example is with multiplication, but we want students to understand, like as an example, 8 times 7 might be cumbersome for some students to memorize, but we're going to help students develop a strategy for knowing that 8 times 7 is 56 through the use of the distributive properties. So there's our strategy, and we're going to achieve that strategy through the concrete. Here's the concrete phase, and you can see we've got 8 cubes going up and down, and we've got 7 cubes going left and right, but I've kind of conveniently arranged these cubes to be a group of 5 and a group of 2, and that when we then change that to the representational phase, we can see that we now have an 8 by 5 rectangle, which has 40 cubes, and we have an 8 by 2 rectangle, which has 16 cubes, and all together we have 56 cubes. And what does this look like abstractly? Well, we can see that we have 8 rows of 7. That 7 is broken up into 5 and 2, and we can see it over here in the concrete as well, 5 and 2. And then we have a rectangle of 8 by 5, and that's right here. And we have a rectangle of 8 by 2, that's right here, right here, right here. So you're starting to see the representation show up in each of the 3 phases. This 8 by 2 is in the concrete, it's in the pictorial representation, and it's in the abstract. And then 40 plus 16 is 56. This abstract is a really essential component to help students develop a deep understanding of their times tables without just relying on rote memorization. Rather, we get to that automaticity through conceptual understanding, and we get there through the use of CRA. In 5th grade, what does 12 times 13 look like in the concrete phase? Well, we're using base 10 blocks, and these outside ones out here are just guides to represent, to help us see that we've got a rectangle right here that is 12 units tall and 13 units wide. So these are kind of like indicators of what the problem is, and the inside is the area model for the answer. And then what does that look like in a pictorial phase? Well, it looks like this. There again, here's our guides, 12 times 13, and then here's our answer. And then what does this look like in the abstract phase? Well, the abstract phase, we don't have to use the standard algorithm. We could use some alternate algorithms that help students see the connections between the concrete and the pictorial representations a little bit easier on our journey to the abstract, the official standard algorithm. So this is a neat, nice little stepping stone. It's partial products, but it's really helping students see that 13 is a 10 and a 3, 12 is a 10 and a 2, and we can see that in the concrete and the pictorial. And that this block right here is 10 times 10, right there. And that these 3 10s right here is 30. And how did we get to that 30? Because we did 10 times 3. We did 10 times 10, we did 10 times 3. And then, oh, what are these 2 10s down here? Well, that's the 20. And we got that by doing 10 times 2. And lastly, what are these 6 little dots? Well, that's our 6 from 2 times 3, which is 6. So this is a partial product. And you can start to see the relationships between these 3 phases of development, this concrete, pictorial, and abstract. So which representations to use? Every grade level has a series of representations that are going to be particularly useful for your grade level. And if you pay attention, these representations form a nice progression from one grade to the next to the next. So the representations that a 4th grade teacher might use are representations that are building upon representations used in earlier grades, and they are preceding and prerequisites for representations used in subsequent grades. So folks, this is just a brief overview of what is CRA Why is it important? I gave you some simple examples of what CRA might look like in kinder, some first and second grade. We did some multiplication for third grade, and we did some multiplication for fourth grade as well. We're going to go deeper into some specific content as we go on in this year. We're going to create additional videos that give you specific examples on specific math concepts that you'll be using in your book. And so I hope this was useful for you. If you have any questions, I'm going to put my email address right here. You are absolutely welcome to send me an email. And actually, I'm also going to include Erica and Veronica on their emails, so that you can email your coordinator if you have any questions at all.